Now, traditionally, people attribute a lot of meaning to the universe, to the point at which philosophers of all sorts had uh, dabbled, well, not of all sorts, but mainstream and many schools of mainstream types of philosophy and some less mainstream all attributed meaning to the world and studied teleology, which is what is the meaning of everything. And the idea is that the bunny, has a purpose. It fits into something that has meaning. Like the bunny rabbits are there to feed the coyotes. The flies are there to rot the fruit, help the fruit rot, and so on and so forth. And this was their purpose. And if you ask me, this is also where the idea of inherent properties comes from. Um, because it's a related idea that you know, one of the purposes of the bunny is to hop. Because whatever the effect of that hopping is has to have a purpose. So somehow or another, that's one of its purposes. In other words, you can turn observable features into purposes to a certain degree. And as you abstract your concepts of objects, and eventually, even if you think not all bunnies hop, maybe this bunny, has an injury and doesn't hop, or if a bunny gave birth to a litter of bunnies and one of them turned out just a fur ball, and let's say by some miracle it was alive, and it was just like one of those little creatures in the original Star Trek. What were they called? Not Weebles. What were they? They were something. And would that be a bunny? It wouldn't hop. It wouldn't do any of the thing, but it would have bunny genetics and a bunny, progeny story, and it would kind of depend on what you were. What the context was. Scientifically, you could easily say, yeah, it was a bunny, odd as that seems. On the other hand, if somebody was selling you a rabbit, you might object to the legitimacy of the rabbit they had sold you. Um, so what happens is the concept of a rabbit then is taken to have these inherent properties. And whether it applies to something or not becomes a separate question. And we just think in this abstract world where, well, bunnies still inherently hop. Sure, one bunny didn't, but the concept of bunnies inherently includes hopping. And what Lakoff and the cognitive science, the second wave cognitive science, linguistics, cognitive linguistics, this whole crowd has totally demonstrated over the last 30 years is that no, it's not like that. You have clustering properties, and if sure, certain behaviors or properties are taken as idiomatic of whatever the category is, hopping for bunnies, being food for predators, whatever is related to our idea of what it means to be a rabbit, a bunny rabbit. Um, uh, Lost my train of thought there. Let's see, where was I going with that? So, you have all of these features and behaviors they'll be related to, but you could think of them as properties, whatever, as I was saying, these examples, these couple examples. And if too many of those properties are not present, then some people will start to say, well, it's not really a bunny. Some people would say that an adoptive mother in the old days might not, well, no, not in the old days, but an adoptive mother might not technically be a mother to some people because there's a crucial feature missing, right? But most people today, at least, would say, of course, that's a mother, but we're emphasizing features that are there, like the motherly affection that a mother has for her children, and if somebody adopts a child and has that kind of feelings for their children and shows that, then of course, uh, we can say, well, that's enough. This other one, technical, whatever, no, and we just usually when that happens, since that's still a category we want to talk about sometimes, we add some word, some adjective, a biological mother versus, and then suddenly this is the real mother and that's the biological mother. Why? Because this one was unpresent and this one adopted or whatever. So, and to be, going into the future, or what's at the edge of the political correctness, at least a kind that, I mean, I think has some grain of sense to it, is that all of the above should be considered mothers, and we should understand this, the way we cluster ideas, or the way we define concepts by clusters of other ideas. So we actually have a concept like mother that is a bunch of, multi-Venn diagrams, a bunch of overlapping circles, or possibly not even overlapping sometimes. That can happen as well. So anyway, people put this meaning into the universe, and then the intellectual elite have figured out that, we did this too much. We put too much meaning in there, and we sort of pigeonholed a lot of things, and its application in society, pigeonholed people, but also we misunderstood nature thinking this way. So we got new ways of thinking of things and how things interrelate and what relationships mean without it having to be a semantic relationship. Because I think we're basically semantic machines. It makes sense that a human, or probably any mammal's reaction to something is to is to abstract it and to try to simplify it into a sort of a kind of a data structure that a semantic machine understands. And so if we're trying to relate two things and we're a semantic machine, we tend to look for a semantic relationship, where the word semantics, it means meaning. Semantics is the meaning of things, and as a relativist, I think that always has to be the meaning of things in relationship to one another. So it's understandable that we project this teleology, and then we figure out, well, we did a lot of projecting there, and so but we overreact, I think, at the moment, where we're trying to pretend that there's no meaning. So we have a model of the world in which the world doesn't actually have meaning. It has relationships and things happen in it, but they have no meaning. And in reality, we have to live like the world around us has meaning. But a headline in the newspaper has meaning or whatever, but not really. And it's kind of like we have a lot of these things right now in the postmodern, meaning the modernism after the postmodern reality, meaning the quantum mechanics and all the weirdness was injected. We're left with, sort of a lot of these things where, we believe determinism. I've been surprised on YouTube how many people disbelieve in determinism. We believe in you have to live like there's not determinism. Well, that's not okay. I don't believe that. I think let's debate this idea that you have to believe in some falsehood for some reason. Well, why? I mean, the lessons of science and its value to technology should be that the more you know about reality, the more you can do. It doesn't limit you. It's not like you can't live as though the Earth goes around the sun. You might find it convenient to still think of the sun as rising and stuff, but most people don't bother with that. They might use the words and the language, but that's it. That's just a remnant. They know the Earth goes around the sun. They're not as clear on the sun going around the center of the galaxy and the galaxy flying in directions that they lose the train there. But anyway, they can, just think of things that way. It's not like, well, I know the Earth goes around the sun, but I've got to think of things as though the sun, you just can't, there's no other way. So it's not okay with me that people would claim that, yeah, I got to live like the world has meaning, but it doesn't really have meaning. That could be true, but if so, it's a claim that needs to be demonstrated. So, with phantasmagoricalism, there's an inherent issue going on here, and it draws from what's going on right now and over the past 20 years, it turns out. But I've really only started following this trend in the last 5, say, of quantum information theory. And the idea, as I would put it, is basically this: that there's a bunch of quantum computing guys started working. And then it became apparent that when you're talking about a quantum system, uh, what makes one quantum system a computer and another not a computer? Nothing, because they get events in the beginning and they get events on the outside, and in the middle they do quantum processes. Now, you could be processing a bunch of random numbers into another bunch of random numbers, but there's some processing going on if you're going to call what a quantum computer might do uh, quantum processing. And since quantum computers have only now just started to be built in the last few years, are examples of quantum computing devices, very simple ones. Obviously, when they thought about quantum computing, they were thinking, well, here's the kinds of things that are possible to do in quantum physics, and they could calculate the energies required and what would go on, and so they could try to do those things, but they hadn't done them. So really, anything that's possibly conceivable, even some that won't be possible in the end because some technical problem will show up, and they'll go, oh, I see. And so the whole array is a part of quantum computing. And the whole array is what quantum mechanics is. And so the only difference between quantum computing and quantum mechanics is that in quantum computing, you look at the photons that come into the system initially as information. You look at that as like reading information, or they are information. And over here, you'd say they were, just photons. You just call them directly what they are. Well, it turns out that thinking about them as information is very, very effective, and it's sort of tautologically true because, the quantum system is processing information. The information is the state, of collapsed wave functions at a particular point in time. Then when it goes into, the kind of quantum processes we're thinking of, which some sort of usually extended, but, some sort of tunneling, entanglement, all of the things that lead to some of the more hard to intuit features of quantum mechanics, then why wouldn't you call that whole system whatever you want? A computer, a physical system, it's one and the same. Suddenly, there's an argument to be made that we have discovered we're in a computer. But really, it's because we've discovered what we meant by computer. We meant something that went logically step by step. And anything that did that, if you called one step the state of the system at one step information, then you would have information processed into another state of the system. And if you called that information, then any physical process can be called a computer. It might not be very good at adding numbers and doing things we use our computers for, but it could be considered a kind of computer with a built-in algorithm, which is whatever the system dynamics are that get it from this state to that state. Right? Now, in quantum mechanics, of course, I love this because what gets to happen in the state transitions is quantum mechanics. And it means that information, thinking of information as physical, which is something as a child I always wondered about. Is information just in our head? Is it real? Is the information out there? Are we putting the information out there? We pretend that there's information because we understand, so there's some sort of data in the mind. And it was kind of invented because of a phenomena, but somehow it's not really information out there. Well, with quantum mechanics, no, it looks like it matters what information is stored. The whole quantum erasure and these kinds of things are going towards the issue of, is the information somehow recorded in a physical transaction that, that's recorded and therefore can be verified over time and whatnot. And if so, that thing's not going to be turned into a lie, and it changes the behavior of whatever energy has been flowing through this quantum system, right? So, so the fact that our minds think of things in terms of meaning, well, what is information? Information is the atomic unit of meaning. Information is always about something else. It's always some Sherlock Holmes thing. It's this fundamentally tiny thing where we're saying, you know what? I see a broken twig. That means someone went by. That's information, right? I see a broken twig. I don't know what it means. That's still information because you're saying it meant something. And there's a billion things around you, many of which you would acknowledge that have some minimal amount of information. You just don't care. But many things that you think have no information, and it's obviously just because you're not taking information from it. Some scientist or carpenter or plumber might look at a part of your house you never take information from. Down in the basement, there's all those pipes. I never sort them out or anything. To me, it's not information. Well, there is just a little bit of information of that's where the pipes are, and some other guy goes down there, he sees more or less, right? So, it's very useful to be able to look at the universe as though it's full of information, right? And there is a rectification between us having over-projected meaning into the world, but also leaving to realize there is meaning in the world. Well, that's where the meaning comes from. There's a reason we thought that's all, there was more meaning there, because things are coming to us from the world. That's where we get all of our ideas. So yes, a lot of those ideas about what things mean, the more abstract it gets, the more wrong it is to put it back out there. But if you try to minimize how abstract you get and talk in terms of material things like photons and particles in this very systematic thing, then there remains the information, the quantum information, and thus you're getting the unification between semantic ideas and physical ideas. For example, entropy, right, a very crucial idea in the history of science, really the whole history of science, and just in every way, it's a crucial thing. I could go on and on. I mean, one is because it's really stand on its own as a third pillar of even the modern systems. And it's sort of an organization of a chaotic system, and the techniques they use have a very interesting history that's worth learning. But anyway, so entropy, very physical idea, though abstract, right? Because when they call it a measure of chaos, it's not quite right. It has to do, it's hard to characterize. But anyway, in the quantum computing version of quantum mechanics, which is 100% compatible with QED, right? It's just that you look at certain states of the system as information, right? And in the other one, you just call it the state of the system. So the 100%, aligned, these systems. So, well, anyway, there's a lot of reasons to to follow this stuff. But what I was going to finish with was, so entropy, which is very physical, is now related to information. It is information you don't have. So when they originally, there's an equation for entropy. I've shown it before, and it's kind of how fast everything's moving and how much you can know about all of that. And it's a way of modeling a gas. When they realize, oh, gas are made of all these little particles, we'll never track all of them. How can we characterize it anyway? Right, but the scientists did think, it's kind of a measure of disorder. But what does disorder mean in physical and a meaningless? Well, in quantum computing, and the quantum computing view of quantum mechanics as the physical reality, it means that you don't have information, that this system has not been impacted with photons from this system, thus it doesn't have information of that system, thus they're in this sort of disconnected state because they have not shared information. When they share physical interactions like sending photons and electrons from here over to here, they start to imprint each other and they start to become connected through this shared information. Right? And so the universe is information, and so a phantasmagorical theory has a big advantage. Because if the world is essentially, every bit of it in the universe, based on bits of information, things interacting with each other, exchange information, energy is information, then, and that's the kind of computer we live in, is one in which little bits of meaning are the little pixels of meaning are are bits of information, and we're information processors, then we actually have a better connection to physical reality than we think. And it makes more common sense that, yes, in fact, of course, this phenomena we feel and experience comes from the universe that is around us. It's not some other thing. It comes from the universe, and it's something that can probably happen at any scale, theoretically in physics, though in reality, to isolate the systems from their surroundings so they're protected, so that certain kind of chemical reactions can happen and this phenomena start. Okay, you might need a minimum mass, a minimum number of molecules. In other words, for a single sugar molecule, maybe there's the potential of this kind of a phenomena, but it's not going to happen because of the shape of the sugar molecule. But it can happen if you have enough million chains of molecules in a membrane that isolates a system that can then compute without being drowned out by the surrounding, entropy. The unknown information becoming known unwillingly, causing the computation not to be possible. So in other words, it's kind of funny. We think about I think a lot about our senses of the world, right? That we sense the world naturally, but our original purpose of having the cell membrane is to block out a lot of information that we don't want because we can't make use of it. It just heats us up because information is energy. So if you get too much information, you heat up, and it might not seem that way to us a lot, but if you're just this big and the information is a light bulb, you're going to dry out, from that information, right? Because the information is the same thing as the energy. It's the exact same thing. That's what we've learned. And if information is energy, then we finally have a place in this universe again.